Our next speaker is David Herald, and David has been asked to speak about the best observations or the most interesting observations other than the North American ones, which Norm presented. Dave Herald is, as you all know, is the author of Occult, the complex software that we all use for our occultation predictions. Dave started with computers back when computers occupied a full room, and he's now retired for 17 years. He was a deputy commissioner of the Australian Patent Office. So we welcome Dave to make a presentation about occultations observed in the last year. Take it away, Dave.
Can you hear me now?
Loud and clear.
Oh, this is good. Now, where am I going? Just bear with me for a second while Okay, is that showing up?
Perfectly.
Okay. It's looking a bit different to what I'm used to here. So anyway, yes, that's the title there. I'm going to go through the non-US results, but there's fairly selective and random selection. But what I wanted to do is, as I've done previous years, is to go through a statistics side of it, so we get a picture of what's happening globally, which is important to understand, particularly for the people that do the reviews and coordination, and also for everyone to have an understanding of where things are developing. So the first slide is just showing the growth in the number of observations we've experienced over the years. The last couple of years has seen a massive increase, which has come about because of Gaia. And compared to back in the 1990s, where uncertainties were, well, there's an event across North America, but it could be down across Antarctica or off past the North Pole, as prediction capabilities now. If it's more than 100 kilometres off, then it's a really lousy prediction. And for some of these things, such as Didymus, prediction accuracy is down rather better than a kilometre. The sense I'm getting from this year is that the massive growth that we had in 21 and 22 is probably flattening off. But it's still too early to say for sure. Yep. Next one, showing the number of events that are unusable. These are observations where, when we do the analysis, for one reason or another, we figure that the observation's unreliable. As you can see, back in the 90s, this was a huge problem. They were all pretty much visual observations. Look, in 1994, 70% of the observations were pretty much false observations. With the introduction of video, starting around about 2000, that has steadily dropped. We're down to a very small percentage here. I should say in my presentation, I'm focusing on 2022 and I'm not including anything from 2023. But it's nice to see that in current observations, we've got quite a low rate of events which are unusable for one reason or another. And I won't go into the reasons for that. Some of it is because of only a single chord with just one of the DNR and not both. Some are dubious results in the best of times. Now, looking at the worldwide situation, I've got here 2022 in comparison with 2020. I won't read out the tables. You can all look at that. You can see that compared to 2020, the number of observations have gone up significantly. For North America, from 300 odd to 500 odd. Essentially, it's sort of, well, not a doubling of observations over 2 years, but a 30 or 40% increase. The interesting thing from my perspective is, you can see that there's been a large increase in successful observations of small asteroids. It's been a feature of the last few years that with the higher predictions and people observing from home, you can get multiple predictions for a night of these small asteroids, and a fair chance, if you have half a dozen asteroids one night, a fair chance you'll get one or two of them, even though they're less than 10 kilometres diameter. And that's seen a massive growth in there. And even in the 10 to 20 kilometres diameter, there's been a growth. When you're looking at the large asteroids, if anything, it's been a reduction. It's pretty much the same. The next thing is when you look at the number of chords observed in an occultation, in an event. Now, remember that to get a half decent measurement of the diameter, you really got to have two chords and they've got to be well spaced. To get a Frisbee firm measure of diameter, you need at least three chords, preferably more. This plots the number of chords per occultation over the last, 18 years. You can see a massive increase in the number of single chord observations, a fair increase in the 2 to 3 chords. When you come to the 4 to 9 chords or the 10 or more chords, particularly the 10 or more chords, virtually no increase. And this is in my view, it's because people are being able to observe more events at their home location, whereas when it comes to traveling to observe events, there's not much growth in that for all sorts of practical logistic reasons. This plot suggests a tapering off in the single chord observations. You'll see what happens for this year. It's a major source of observations and almost all small asteroids. Now here's a interesting statistics. The top one is a statistical analysis of the number of observers per event. Now, this is per successful event, not all efforts put together. But on average, with every successful event, on average, there's 2.0 observers per individual event. And most of those are tied up with multiple chord events. The other plot is the number of individual observers that we have each year. And find this sort of interesting. It's not a uniform year plot, but 2010 we had worldwide about 530 observers. The last 5 years or so, we've been running around a bit over 400 observers. 219, we had almost 500. It's interesting in that the overall number of observers is fairly constant, fairly static. And our administrators can perhaps reflect upon why that's the case, why our number of observers are not increasing. I have my own personal views, which is associated with social media type nonsense that happens these days. But it's an interesting thing to see that we're not getting, on the whole, an increase in observers. New double stars, I want to say a bit more about this tomorrow. Well, that screen is self-explanatory. The separations are much smaller than most normal double star observers are dealing with. One of the characteristics of our observations is that it's not necessarily a unique solution, but you can get 2 solutions or 4 solutions depending on number of observers you have involved. A single chord, a single observer with a double star can finish up with 4 possible solutions. And I should add here that when those results get into the Washington double star catalogue, only one of those will appear in the online version of the catalogue, but in their systems, all 4 solutions are maintained. And the separation have an uncertainty of less than a milliarc second, which is pretty good. Now, 2022 was a fairly active discovery of double stars. That's 16, I said 15 there, but there's actually 16 double star discoveries. You can see the basic parameters there. This is an area, again, I'm going to speak to tomorrow. As far as I'm aware, none of those have gone through to be reported in a way they'll get into the Washington double star catalogue, which from my point of view is highly undesirable. And as a group, we need to be able to recognise the discoveries that individuals make. And that means there's some effort needs to be required, and I'm going to talk a bit about this tomorrow, about how we get our double star discoveries into the mainstream official recognition type category, because our discoveries are quite unique. We're in a separation range which is too small for the normal traditional double star observers, and you're down in where speckle interferometry, some of these speckle interferometry is not even adequate to separate the components. An important area of what we do, peripheral, and we're not doing it well. Now I'll run through a number of events from regions around the world other than Australia, North America. Here's an interesting event of Peraga, however you spell it. I'm like Norm, these Greek mythology figures. My pronunciation's pretty crap. This is interesting because you've got a clear chunk taken out from here. Here's a light curve. I wish people would be more proactive in submitting light curves, because with a cult, if you've got the light curves there, you display the event, then all the light curves become available. You can see what's going on, and you can see from this, whichever light curve that is, I forget which there, a very clean occultation event. Very easy to see what the quality of the light curve was like that's been analysed. A fit to the shape model, 110 kilometres. There's this satellite diameters. And what I've started doing, and I'll talk briefly about this tomorrow, where we've got shape models, fitting, looking at the results from all the fits to a particular shape model, deriving an estimate of the diameter. And for this one, fitting from all 4 events where we've got decent results for this asteroid, we get 96 plus or minus 2 kilometres diameter, which is interesting given this one, a fit comes out as 110 kilometres. Now down the bottom, I thought I'd show this as, again, I'll be talking about more of these issues tomorrow in terms of my role as a global coordinator or whatever. This is an observation done very recently in the last month of the same asteroid. 3 nice chords there. And here we have 1 chord there and another chord there. And I got engaged in some discussion about this, and this is a profile plot where people involved, or certain people involved, were quite adamant that this was a uniquely shaped asteroid, that the 2 chords in question, the top 2 chords in question, were definite and real. And they were proposing some sort of shape like this for the asteroid. It's fascinating when you look at the light curve for that, which I'm not going to show. The magnitude drop was 0.1 of a magnitude. And yes, there were some drops at the right time. Were they real drops, or were they just coincidental noise? I let people draw their own conclusions looking at what is proposed there for an interesting shape of an asteroid. A flying duck, I think that looks like. Here's a nice observation from memory. You'll notice this chord here is an angle to the other chords. When that happens, that's an indication that observer's a long distance away, typically in a different continent from the other observers. Quite a reasonable fit to the shape model. The shape model's not perfect, but that's fine. And you can see here our diameter and the satellite diameters are basically quite consistent. IRAS is clearly too small. Those 2s are okay. Here's one which shows a Japanese observation, an asteroid with these 2 possible shape models. You can see they're quite different appearances. the chords will happily fit both. One of the things which worries me when I look at situations like this, and on this picture, it's probably clearer in this one. Here we have 4 chords. Those two are consistent with each other, and that's sort of consistent with that. But you've got this chord in the middle. And you notice you've got a curve like that there, and a curve like that there. My question for people to think about is that situation caused by a mountain on one side of the asteroid, and hey, the shape model doesn't have that level of detail. Is that caused by a mountain on that side of the asteroid and a hole, corresponding depth hole on this side of the asteroid? Or is there a time-based issue where that chord has got a time-based error, and if it was correctly positioned, would be back consistent with the other chords? My problem with this is that, well, it's a problem in itself. To me, the statistical probability of having a mountain on one side and a corresponding dipole on the other side is pretty low, and I see this situation too often. Or is there an issue with our reliability of our time base across all our multitude of observers? And this situation gives me cause for concern about the reality of our accuracies as reported that come through the system, that many are very good and consistent, but there's a small number that, for whatever reason, and we don't understand why, there's a problem. There is a likely problem with the time reliability of the observations. And we as a group, particularly those that focus on extracting light curves and measuring them, or setting up systems to record these events, probably need to do a bit more of a focus on looking at past observations. They're all available there, looking for situations like this, or inconsistencies, obvious inconsistencies in chords, and asking the questions from the data extraction side, why is this so? Because I don't think that reflects the real shape of that asteroid. And this is another one like that. This is a non-unique situation. When you look at these chords, this side over here is all well defined. This is the disappearance side, all well defined, all very plausible. Reappearance side, these ones are consistent. That one there, is that okay? Or maybe should be pushed back that way, or is that observation late? And then you have this chord, and that reappearance is terribly late. I should add that from my experience in following up these events, this type of situation where lousy times, I mean, that chord's definitely wrong as far as I'm concerned. When you start looking at the light curves, the typical thing is the light curve, or the video observation, is really lousy, like the signal of the asteroid is very much buried in the noise, and you finish up having an unreliable interpretation of the light curve. And I see this with results coming from all light measurement tools. This is there's two shape models for this event, and this is the second shape model. In this chord on this model is totally out of this world. That's more consistent, but with this shape model, you could see that that's a time-based error. You could move it back there and it would fit nicely. So of itself, here you have that chord and that chord. Is it a false reappearance and consistent with this model, or is it a time-based issue here, consistent with this model? And that chord by itself has the capability of saying one or other of these shape models is incorrect. But the possibility of a time-based error excludes that as a useful observation from determining anything about these two shape models. Effectively, that observation is useless for any meaningful analysis of the shape models and the astrometry, and that is certainly useless. Now the next one, Tolosa. Again, these two chords out here. All the other chords nice and consistent, and then you get two chords like this where the reappearance is clearly. When I look at that, I have no doubt there is a problem with the measuring the light curve for both these chords, because you're not going to postulate a mountain there and another mountain there. That's bad data. I haven't been talking much about these, but these show that these are typical diameters that come from the satellites with their uncertainties. We have a smaller uncertainty and a more precise diameter when you can fit it to shape models. Now here's an interesting thing. Again, a nice light curve from one observer. So it's a nice, clean event from this one. In Europe, they had successful occultations by Ohio, a week and a half apart or 2 weeks apart. And you can see that in both events, a very nice fit to the shape models. It's the same shape model, different orientation, and the chords give a very nice fit. Here we've got some difference in detail down here, but the shape model's pretty good, and we get a very good diameter measurement of that, although the very similar to basically the mean of those values, but our uncertainty is much smaller. Here's one that observed in Europe. Tim, I noticed Tim is one of the participants. He's been very good at providing light curves for his events, and here you can see that this was a low magnitude drop event. And here's the fit of the chords. You've got the uncertainties are relatively large on many of these. I mean, that's got a small uncertainty, but this one's got a large uncertainty. It is a pretty good fit to that shape model. From 18 events involving Kalliope, my analysis of the fits to this shape model, give a diameter of 150 plus or minus 6 kilometres. That uncertainty is much less than any of those. And it ties down the diameter much better than those values there. Of all of those values, the Japanese Akari AQA value is the closest to what we're getting. Whereas 181 plus or minus 19, that takes you back to 162, rather large than this. Neo-wise, 157, which is still larger than that. And must be getting towards the end of this. Here's another one from Europe, a very nice fit to the shape models. And I haven't displayed the fits to two shape models, but here we have a fit to two different shape models. This one had more events capable of fitting of it. That one, there was 3 events where the occultation appeared to be inconsistent with the shape model. 160, 466 plus or minus that. Again, quite a bit different from these. But that's quite a nice observation there. I should say, in context of these multi-chord observations, it's an interesting distribution of how they're being observed in our 4 main regions of Australia, Europe, Japan, and North America. Australia, our observer density is so low, we're so scattered, that getting multiple chord events involving more than 2 or 3 observers is extremely rare. In Europe, they've got a high density of observers across Europe. Travelling to do group observations of an event is, from my perception, almost non-existent. People tend to observe from home, but because of the density of the observers in Europe, multiple chord events are not uncommon. Japan is an extreme example of that. Small landmass, large number of observers, and a large percentage of their observations are multi-chord observations, but they just don't get as many observations or as many events observed as anywhere else because of the small size of Japan. In North America, my perception is the majority of multi-chord observations come from planned efforts to send observing groups to observe these events, rather than having multiple chords from multiple home-based observations. It's an interesting difference between the regions. Here's a nice one from Japan. Very nice fit to that shape model. And the reappearances look good. That chord there, you could wonder whether that, given those 2 chords there, is there an indication of a dip in the asteroid, or is that indicative of a timing uncertainty in the time of the reappearance? They're fascinating questions, and to draw conclusions about the shapes of the asteroids, we need to have absolute uncertainties, real uncertainties in the event times, limits what conclusion you can have. And when you have a large difference with chords closely located, then, in my opinion, you have to wonder why. Is that chord too long? Is that chord too short? It's the why is the difference between the chords. Is it a chord length issue, chord positioning issue, or a shape in the asteroid? And of course, we want to say it's a shape in the asteroid, but in situations like this, I'm not confident enough in our processes to say that that's definitely a shape in the asteroid. Here's another nice one. Again, you can look at these. This is from Europe. You can speculate on the reliability of these chords. You look at these three here, never mind the ellipse. Compared to those two chords there, that chord seems to be displaced in this direction. Question, is that a mountain on this side, valley on that side, or is that a time-based issue for that chord? Or is there a time-based issue for this chord? This is a sort of thing that I see, which raises questions with no answers, and leads me to be occasionally ask questions of any measurement tool. And this is a nice one, the small asteroid Phaethon, however you pronounce that, only 5 kilometres diameter. From previous occultation, 191. I obviously didn't update that figure there. That's a nice result with a very small asteroid where you get a clear effort to do it. The chords here are all consistent and a very nice result. And I'll leave it at that and I'll stop sharing and take questions.
There's a question for you in the chat group from Joel Castro.
Okay, where do I get the statistics? From Occult. On, let me
Thank you
bring up the screen.
Dave.
Hey?
Thank you in advance.
I'll just I'll bring this over, and I think if I put it there, I'll shove it over here and I'll share the screen again. Where do I get the results from? Here's Occult with the asteroidal occultations. Down here, there's this button here, Statistics and Occulted Stars. And I'll just click on that and you get this form, and click this button here. And there's a list of what's been observed so far this year that's got into my system. There's a list of all the asteroids we've observed. And here's a breakdown of the observations by region and the number of observations in there. You can get the number of asteroids observed in more than one occultation. There's a whole heap of those. Stars observed in more than one occultation. There's a lot of these are fairly bright, relatively bright stars, but some obscure stars. And from here you can get a count of the occulted stars by magnitude range. This is over the whole period of the data set. So you can see that we've only had 5 occultations of stars brighter than 2, and 4 of those were of Regulus. And here, a list of the bright stars occultations that goes down to 6th magnitude. And then you can list all observers. That's just bear a second, and you can. I get here here's a list of all the observers. Who asked this question?
Me, Joel Castro from Mexico.
What was your family name?
Joel Castro.
Quattro.
Well, thank you. I see from where you landed.
Yeah. So there's a whole heap of statistical data that you can get out of there. The other thing I think it's useful for me to show at this point is observations by an observer. And let me pick a random thing. Oh, I'll take Norm Carlson. You don't mind, Norm, do you? Put in his name or part of his name and a list all of his events. Here you can get a list of all of the events that Norm's, all events which have resulted in somebody observed a positive event. These are all the events that he's observed there. The left column is a count of his successful events, and this column is a count of the number of sites that he set up in all of that. So Norm's had 43 successes, and that's from 64 sites. And here, there's a list of his sites and the number of observations from each of those sites. So this site here is where Norm's done most of his observations, 17 of them. But otherwise, Norm, you must have been on the road a fair bit.
That's for sure, yes. That's almost discouraging. Okay.
Now, one of the things Dave Galt and I have been having to deal with over the last few years is lousy site coordinates. You go through the thing. Occasionally we get site coordinates without where it's an error by several degrees. When those things happen, it's degrees, minutes, seconds, you name it. Being able to have a look at where observers have previously observed from, we can often pick out the keying error that gave the wrong site coordinates. And yes, we get back to the observer and say, hey, is this where you observed from? But this is a useful tool for us coordinators, and that's Norm at his level, and Dave got myself as when there's a problem chord, and you plot the events where the observers are in Google Earth and find somebody's in the middle of the lake or in the middle of a forest. And yes, this happens all too often, actually. Then we can have a look at their past observations and figure out where they actually were.
David, when you show the shape model with the observed chords superimposed upon it, you also show the uncertainty sizes at the end of each chord. What is the uncertainty significance that uses? I mean, is it 1 sigma, 2 sigma, or what?
It's their reported uncertainty.
Well, we report 1 sigma and 95% and so on, 99% or 99.7%. So do you know which of those values is being used in the diagram?
It's what comes through. It's in the peyote, it's the default.
I think it's done to 95% probably.
Yep.
because I think they consider that the most important. But sometimes that can be significant in comparing the chords, I think, to know just what that uncertainty is.
I think iota uses that value as well. The other one is lie moving. I think that's a similar thing that I can't remember for sure. I don't see any common differences between the measurement tools on that score. The greatest variation in the length of that uncertainty you can associate with exposure durations with integrating cameras and things associated with signal to noise. Overall, the issue of the uncertainty we get with our observations is an area which, in my view, merits further investigation. The problem with all three of our main tools is that our assessment of the reliability is based on largely a theoretical aspect. We can generate synthetic light curves and extract them from it. What, to my best of my knowledge, we've never done, and perhaps Bob can correct me if I'm wrong, but I've certainly it or I haven't done it, is to have multiple observations with completely independent recording setups of the same event, and lunar events is probably the easiest one to do, with telescopes set up pretty much at the same location, independent setups, record an event and analyze them all independently and see what the differences are. This provides a real test of the data and not a test based on synthetic approaches. Now, let me go a little bit further here. This is, from my perspective, an important issue. And it takes me back to the first, I think it was Apophis event, which we had success with in the States. For this particular event, we had three predictions. There was one generated by Mark Bowie, which was Larry Wasserman was the author of the software. There was my prediction, and there was, I forget, there was a third prediction. I think there was even a fourth prediction. Everyone was convinced their prediction was correct. When we had the results of the observation, everyone's, and I mean everyone's, prediction had defects. There was hidden problems with every prediction. And all of us had to delve into our code and find the cause. So that says to me, for our observations, it is all very well for any of us in any of our tools to say, we believe we are getting the best results possible, and our results, they're spot on, they're accurate. But are they? That's an underlying question. And I think there is room, when I see the results coming through and the discordances you occasionally see between chords, I would say that there is something going on there, which could be observer issues, could be failure to apply camera corrections, there could be analysis issues. But my direct experience on the prediction side was, no matter how good you think your results are, until you're in a position of assessing the results in a real environment, then you are your basis for saying my results are perfect are somewhat restrained. They're limited. I mean, there needs to be a way of assessing the accuracy in a real sense rather than in a desktop sense. So that's a challenge for Tony and Bob and whatever, as to how you get past the doing a desktop testing to actually testing in a real life environment. And I mean, lunar occultations with half a dozen setups in somebody's backyard would be an ideal way of validating the tools and the various corrections that one might apply with different cameras.
Thank you for those insights, David. I'd like to move on now